Alright, in this video we're actually going to look at why atoms have spectra using both the Bohr model and the quantum mechanics models we learned about. And we're going to start with the quantum mechanics. So here I have three different energy levels for you. Remember, each energy level we give a number of 1, or rather a variable of n. So n equals 1 has an energy level, n equals 2 has an energy level, n equals 3 has an energy level. In these energy levels, we have different orbitals. We call these L's. So L of 0, L of 0 and 1, L of 0, 1, and 2. And in these energy levels, they are split by m sub L values, as shown here. Okay, so that is how the energy levels look like, where low on this chart is low energy, good. High on this chart, high energy, bad. Alright, so let's take a look at the spectra. So we know that atoms will give out certain wavelengths of light. And we know now, or at least is hypothesized, that these waves of light have to do with the distance between orbitals. That is, electrons are jumping to different orbitals and they'll let off or absorb light because of that. So we say an electron is excited if it transitions from a lower energy level to a higher energy level. And the reverse of that process, if an electron goes from high to low, we say an electron relaxes. Okay? Now, when an electron relaxes from high to low, it releases light, which we see in the emission spectrum. And when it's excited, we see it absorb light in the absorption spectrum. And the distance between these two energy levels, that is either relaxing from or being excited to, is the same distance, so it's the same energy, so the wavelengths of light are the same in both cases. Okay? And we can think about this in either the Bohr model or the quantum mechanics model. It works either way. But basically, it is the light you see is the energy difference between the gaps it is jumping to or being relaxed to. And the reason why we see light come off at all is because electrons hate being high energy. They're very unstable. So if you shine light at an atom and that atom absorbs light, that is, an electron jumps from low to high, it will only be marginally stable, if at all stable, in that high level, and so it will want to drop down and emit light. And each line, like I've said before already, each line in this emission and absorption spectra is just the energy difference between our two levels. Alright? So, predicting what a hydrogen looks like. With all this information, we can now predict what kind of absorption and emission spectra we will get. In both the Bohr and quantum mechanics model, since we're only dealing with hydrogen is super simple. Both of these models can predict our spectrum. Like I said already, energy is absorbed if you jump up to a higher energy level, and light is released if you drop down from high to low. And the amount of energy is given by this equation, where the energy of the electron is the final state minus the initial state, and the energy of the light that is being shown is equal to the negative energy of the electron. So if you know the energy of the final state your electron is jumping to, and if you know the initial state where your electron began, you can predict how much energy you need to shine at your atom to make this energy jump. Then the energy that you get out is just the negative of this value. And we can use an equation for this, where we have the energy of a photon is equal to Planck's constant, speed of light divided by wavelength, or it's equal to 2.18 times 10 to the minus 18 joules multiplied by 1 divided by n final squared, that is the energy level you end at, minus 1 divided by n initial squared, or the energy level you begin at. So using that knowledge, let's say we have an electron that's at energy level 7, or n equals 7, and we're the hydrogen atom, and we relax to a lower energy level. The light that we emit is 397 nanometers. So the question is, what energy level did we relax to? Here are the constants you need to know. I have the joule here in scientific terms, scientific units. So all the information you need to solve this is on this slide. So take a few minutes, see if you can solve this. Come back to the video when you have an answer. Alright, so let's take a look at this. First, let's just fill in our constants. So we have Planck's constant, we have the speed of light, and we have our wavelength. Our wavelength need to be in meters because we have Planck's constants in meters. We want our units to all work out. And we have, well, our initial state was 49 because it was 7 squared. And here's our final state. That's our variable. Okay. So what I'm doing here is I've just gotten 1 minus n squared final minus 0.02. So all I did was distribute this 2.18 times 10 to the minus 18 to each part of this equation, solve this part of the equation numerically, and then I had 2.18 times 10 to the minus 18 over n2 final, so I just got n2 final alone. And when I add each side, then flip the fraction, I get 4 equals n squared final. Solve for n squared by square rooting each side, and I get 2. So for this, you need quite a bit of algebra to be able to solve this problem. So I do highly suggest, now that you see the answer, try to cover it up, redo this problem, and see if you can follow along with my math. Alright, so that's it for this video. See you in the next one.